Okay, this is a clip of the collapse of the North Tower of the World Trade Center taken by BBC World. And I was just introduced to this video fairly recently, and it's quite remarkable in what it shows. Just before we get started here, notice that we see material being ejected on the right side of the building here at this level, even though up here the building is still intact. And so it's a number of floors below the actual point of collapse. Actually, the actual point of collapse appears to be much higher because material is coming off from up here, and yet there's also material being blown out the side. If you actually watch the original clip of this video, which is available, I believe, on YouTube and elsewhere, you'll see that this material is truly coming out to the right. It's not just a perspective effect of some kind. Okay, what we're going to do is I'm going to follow this blob of material. I'm picking it because it's nice and conspicuous both in this frame and throughout all the frames of this video clip. And I'm going to compare it to the leading edge of this ejection of material down here. And the question we want to ask is, we're having a race between the two. How does this progress down the building in comparison to something that's actually falling at free fall through air? Okay, so we're using Physics Toolkit, and Physics Toolkit allows us to put data points, so I'll put my first data point right there, and then as we step through, I'm going to be able to make some sense of this. Okay, so we're doing the grungy part of science now, which is you have to do the boring work to get the data. But this is going to be relatively quick. And okay. By the way, to get the scale for this photograph, I'm using the width of the Trade Center, which is 64 meters. And that can be used to compute a scale factor for the picture. Let's look at this in comparison to the previous one. Okay, we are now finished with data set 1. Let's go to data set 2, and we'll put little green dots over here. So I'm just using the bottom edge of where the material is pretty clearly being ejected. And so like right here. There's actually looks like some precursor activity going on even a little bit lower, but I'll just be conservative here and take this point where the material really starts to flow. So this isn't a single object I'm tracking now, it's a wave in the sense that the material from here went out already and this is new material, but it's the pattern that's moving down the building. So we're tracking the pattern down here in relation to this actual object up here. Okay. There. Okay. We have the complete progression now. Okay, let's look at the data analysis. We're going to choose option 9 for relative motion. It's the motion of it's the race that we're interested in, not the actual speeds. We have a moving camera, and it's going to be very difficult to get any useful data out of that kind of thing. However, the relative motion should stay valid. We're going to choose Y direction, which is vertical. And we're going to look at data set 2, which is the wave, in relation to data set 1, which is the object falling through air. And we're going to look at position versus time. Okay, let me move this up a little bit here. Okay, notice that we have a fairly horizontal trend at the beginning. A horizontal line would indicate that the position of one is keeping equal distance ahead of the other. So in other words, we picked an object which was higher than the leading front of the wave, and so the wave front is like 35 meters lower. And notice that at the beginning it actually is getting less than 35 meters in front. So in other words, when it goes uphill like this, it means it's losing ground. So it's going a little slower than the free-falling object. Then it turns around and it goes faster than the free-falling object, coming back down. So on the average over this first half of the run, it's staying pretty well equal to the speed of the free-falling object. And then it jumps ahead. Remember, this is not an object that, so you'd say, how can it jump? Well, the explosions start happening sooner. So they start coming out from the building even lower. So there's a point at which you actually have the explosions jumping ahead of the motion of a free-falling object. And it's fairly constant at the end as well. So in other words, you have on the average the wave coming down the side of the building even faster than free fall. If the wave of explosions were caused by simply the collapsing building, this would be rather paradoxical. You'd expect that material would fall through air more easily than it would fall through mass of steel and concrete. However, what we're seeing here is that it's keeping up with, on the average, and then in fact getting ahead of something which is falling actually through air.